Hello and welcome to the Engineering Dynamics Course Companion. This is class 15 in Kinematics of Rigid Bodies, and we are dealing with the velocity analysis using the Instantaneous Center of Rotation. Now, I always think this is a little bit of a refreshing class because class 14 is some tough, difficult stuff. But this is another method to do a velocity analysis. A little different, a little easier once you get used to doing it, right? So as always, if you want to skip to the example instead of going through some of this, the B.L.U.F and the explanation of the instantaneous center of rotation, you could go to the links below and jump through. So the bottom line up front, at any instant, there exists this imaginary point, right, for a rigid body called the instantaneous center of rotation. And it appears about that point, at that instant, that the rigid body is rotating about that point, right? And it's found from the intersection of lines that are drawn through the points and perpendicular to the velocity, right? So if you have multiple points, usually two, on a rigid body, look at where the velocities are traveling, draw lines perpendicular to them, and where that intersects, that is the instantaneous center of rotation. And it doesn't necessarily have to be on the body, and quite often it's not. It's some point off in space. And once you find that point, once you find the instantaneous center of rotation, it makes it really easy to find the velocity at any point, because you could find the angular velocity from the points that you know, and now using that angular velocity and the distance from the instantaneous center of rotation to the miscellaneous point that you want to find, you can, from multiplying that angular velocity and that distance, you can find the velocity anywhere. So it makes it pretty convenient. The only hard part sometimes is going to be the geometry. That can be a little challenging. All right, so here is some diagrams kind of to visualize this thing, right? We know that translation and rotation, and that velocity in rigid bodies, or all motion in rigid bodies, can be made up of a combination of translation and rotation. Where now you could pretend that it's in pure rotation about this point right here by identifying it, right? And okay, so here is the one that was close to what we had previously shown in other preliminary setups to the thing, where you can see the velocity of B and the velocity of A. You can see a line that's drawn through those velocities intersects at a point, and that's the instantaneous center of rotation, right? So there's a couple different ways, a couple different scenarios that might happen, right? So you might know the velocity of a particular point, and you know the angular velocity. If you know those two things, well, you draw the line that's perpendicular to the velocity, and you know that it lies along there. And if you know the angular velocity, you know that it's got to be on this side, not that side, right? It can't be on that side. It has to be on this side in order to be able to create that velocity right there. So from that, you're able to find what that value is along that line that's perpendicular. Another scenario, maybe, where you might have two velocities. You might know the velocity at each of the points on the rigid body, and now you could just draw the lines through them and find where they intersect. That's the ICR, the instantaneous center of rotation. And then from the geometry, you're going to be able to find what those lengths are going to be. And then from either of those lengths, you'll be able to find the angular velocity, right? What could potentially happen, right, is that now, in the case, sometimes the velocities could be parallel to each other. If they're parallel and equal, there is no rotation. And so the instantaneous center of rotation would be infinitely far away from the thing. Because if something is in pure translation, did I say pure rotation? I meant pure translation. If the points are equal and parallel, this thing is in pure translation. But if they're parallel but not equal to each other, there will be an instantaneous center of rotation. and it will be somewhere. Either it could be a line that's below there. Now you could see that this right here, the magnitudes drawn to scale will form a triangle in this way, or they could cross like that right there, and then the ICR is going to be right here on the body, right? And you could find the lengths by way of finding here you could do it by geometry, right? And then from that, you could find what the angular velocities are going to be. Now, here's a couple scenarios that we could run through. Here, this is a mistake that often happens. People might pick like this point right here, right, onto the thing. You got to remember, you have to draw the lines that are perpendicular to those, right, to the velocities, and that's going to determine the ICR, right? On a wheel, something that you might try to remember, if when a wheel is spinning and it's in contact with the road and it doesn't slip, then the velocity of the point in contact with the road and the road, there's no relative velocity. If there's no slipping, that point has to be equal to the velocity of the road, which is 0, right? So the ICR, by definition, is the point on the body where the on or around the body where the velocity is 0. So it ends up being right there at this is only for the no slip condition. That's where the velocity of the ICR is going to be, right there, right? So you could find if you know the rotation right here, or if you knew this velocity right here, you could find the rotation because you would know what the radius of the wheel is going to be. But now that you could find the velocity at any point right there, simply by finding the distance to that point and multiplying it and then drawing it's perpendicular, and then you could take that distance and multiply it by the angular velocity. Okay, so now we have something. This is called a 4-bar mechanism in mechanisms, and it's called a 4-bar because the point between there's a imaginary bar, we call it the ground link, that's between A and D, right? But if you were to look at the velocity at A, or the velocity at B in link AB, you would see that it has to be perpendicular to the link itself. And the same thing would be true on CD. Its velocity, no matter whether it's moving to clockwise or counterclockwise, it has to be at C, but through the line that's perpendicular to C and D. Therefore, the intersection of those perpendicular lines has to be down here where the lines drawn through the links intersect, right? And of course, you could find what that omega CD is, right? So there's 3 different angular velocities that are going to be taking place. And this one, BC, is actually for this link right here. So this is often called the crank. This is often called the rocker. And then this is also called, this is the link that's in between the two. I'm trying to remember what the name of it is right here. It escapes me for some reason. Coupler. That's the coupler, right? So they call them coupler curves when we go in and look at some analysis. All right. So here's like another link, another 4-bar with a different arrangement. And you can see here's where the ICR is going to be. It's going to be up above. And so you can see that how that thing is rotating. It's also interesting, it has to rotate about the ICR. So we know this direction, therefore we know that direction right there. And then we also, from here, know what this value is going to be, right? Because it's rotating about here and it's by that. So therefore we know this rotation right there. Okay, so we have to use the geometry to find the instantaneous center of rotation. And so I decided to set up a generic problem here. I think it's very similar to the one that I set up in the last class of a generic problem for the 3 diagram method. Just to show you some of the difficulty for the geometry. You have to take a case-by-case basis because there's not any perfect method to try to memorize. It's not worth trying to memorize. You need to think your way through these problems. But anyway, in here we could draw where that ICR is going to be. And by the way, it really helps to make a scaled drawing, a really nicely neat made scale drawing of these things to try to keep track of the stuff. And you could also even test whether the answers make sense based on your scale drawing of the vectors. So here is the diagram. Really the difficult part of this is breaking the thing apart. So I've broken the thing apart in a little bit more into angles right here to find this geometry. So I can find this angle right here, right, by taking 90 and subtracting out this right here, right? So we could say that this is theta AB right here, right? And we want to subtract out B, and that's going to what that's going to do is that's going to give me this little angle right in here, and then we could subtract that from 90 degrees, right? There's probably other ways that you could approach this, but hopefully you can see that's how I would find this this angle. We could also, up here, we could also find that angle by theta A, 90 minus theta A, right? And we know that this angle right here has to be the same as this right here. So what we could find is this angle is going to be those two combined, right? The theta A plus theta AB, but then we're going to subtract out 90 degrees from it, right? Because that's this 90 degrees right there. So we have this total angle right in here, but we're subtracting out 90, so we're able to find this angle, right? So there's a lot of that. Hopefully you can maybe make the video go back to double check what that is. And then lastly, once you have those two unknown angles, right, those two angles right there known, you could find the third angle beta, right? And you could use the law of sines to find the distances of each of these, right? Because you know this distance, this length right here, so you'll be able to find this length, and then you'll be able to find this length from that using the law of sines once you know the angles. And this is not universal. You have to be careful to work through these problems. So this is a generic one. A lot of times if things are aligned with one of the axes, it greatly simplifies the problem. All right, so here is the problem that we did in the last class, but now we're going to use the instantaneous center of rotation. This thing has wheels that are stay in touch with the horizontal and vertical surfaces at points A and B. They remain in contact, and the lengths are 4 feet and 6 feet. So there's 4 feet here and 6 feet, and this angle is 25 degrees. And then we know that this is 1.5 feet per second downwards. And we want to determine the velocity at point C, right? So we set this thing up right there, and we take a look at this, and we can see, we know the velocity at A is going to be in the horizontal direction, so its perpendicular point comes down to here. So this is a relatively easy instantaneous center of rotation problem right there, because we could just from simple math we could find what those distances are. So the RA with respect to ICR is just the 4 times the sine of 25, and RB with respect to ICR is just 4 times the cosine of 25, right? And so now you can find the angular velocity just by taking the known velocity of B and dividing by the RB with respect to ICR, and now you get that 4.138 radians per second, which is what we found in the previous class. And if we wanted to know the velocity of A, which wasn't asked for, so we didn't necessarily need to know it, we take the angular velocity and multiply it by RA with respect to ICR. So we get 0.6995 feet per second, which is what we got before. Now this is the difficult thing. We got a little more geometry to go on here. We had to find RC with respect to ICR. We already have the angular velocity, so that's good. But now we need to find that RC with respect to ICR. That's going to allow us to find what the velocity of C is going to be. And we're going to predict that the velocity, it's going to be in that direction right there, right? Because It's got to be perpendicular to RC with respect to ICR, and we already know the direction it's going clockwise. So, but now, the way I did is I drew another diagram over to the side because it was very cluttered right in there, and I found that I have enough information to be able to find RC with respect to ICR. What I can do, as I've shown here, is that I can take the square root of this length right here and squared plus this combined length right here squared, and I'm able to find what this total length is going to be. I could also find the angle here in a second. But anyway, I find the value just by multiplying that length times that omega that I found up above, right? And then I have to do a little bit more work to find the angle of the thing, right? So that's just going to be theta c in this case right there. And you want to make sure you're drawing the thing out to convince yourself that that's going to be the correct angle for the result. But here we go. We have 3.89 feet per second at 74.4 with respect to horizontal down in the third quadrant. So there you go. There's the ICR method. It's I might have made it sound more complicated than it is. Hopefully I didn't. I'm trying to make it simple. But the best way to understand these problems is to work through them, do a lot of the problems, and it'll become a lot easier to digest and then own. I think you'll find that ICR is a little bit of a refreshing break from the previous topic. But we're going to start with acceleration next, which unfortunately is quite harder and where students often struggle. So let's try to do our best to try to digest it. So thank you, and see you. Let's say, well, I didn't go to the last slide here. So for more examples, please check out the Engineering Dynamics Course Companion, Parts 1 and 2, available from Morgan and Claypool Publishers. If you come down and you follow the links below, you can go to the publisher. You can also find it at Amazon. Please make sure you subscribe to the channel to see things as I update them and put in more and more content. So thank you very much.